Hello friends, today I will discuss about slope deflection method. Okay, so generally slope deflection method is used in case of indeterminate structure. Okay, that what is indeterminate structure? Indeterminate structure is nothing but that structure which cannot be solved by using the three equilibrium equation. Okay, that is called indeterminate structure. So what is indeterminate structure? I already discussed in my previous lecture. Okay, so today I will discuss about slope deflection method. Sometimes it is called displacement method or stiffness method. Okay, displacement method, okay, and stiffness method. Here the two factors, that is the delta and theta, is associated with this slope deflection method. Okay, so suppose, so I will not derive the formula for slope deflection method. Okay, I will discuss just a procedure and how we apply this equation in case of indeterminate structure. Okay, suppose here a beams A, B and C. Here is the hinge support, here is also another hinge support, here is also another hinge support. Okay, so suppose we are taking the section A to B, beam section A to B. Okay, for A to B, here will be a fixed end moment. Okay, FEM, that is a full form of FEM, is fixed end moment. Fixed end moment, it is A to B, AB means A to B, it is the AB, FEM AB, from A to B. And another moment will also act here, FEM BA, that is from B to A, okay. So now I will discuss about this equation. So for the point A, moment will be MAB from A to B, MAB equals to FEMAB, fixed end moment from A to B, plus 2EI by L. L is the this span length L. Okay, for this span, okay, EI by L plus 2 theta A plus theta B minus 3 delta by L. Okay, and now in case of MBA, it was from MAB from A to B and MBA from it is B to A. So FEM BA, fixed end moment from B to A, plus 2 EI by delta plus 2 theta B. Okay, 2 theta B plus theta A minus 3 delta by L. Okay, so now here I will discuss the sign convention for the fixed end moment. So suppose the beam is here AB and it is fixed at its two ends. So in this ends, one moment will generate in this way, it will be clockwise. So clockwise moment is always positive. Clockwise moment is always positive and anti-clockwise moment is always negative. As well as anti-clockwise theta, okay, rotation will also be negative, and anti-clockwise displacement, anti-clockwise delta will also be negative, and clockwise delta, clockwise theta and clockwise moment will always be positive. Okay, now I will discuss some standard case for where suppose it is a fixed beam having length L and it carries a load W kilonewton per meter length. Okay, so fixed end moment will be WL square by 12. As it is anti-clockwise, that's why the sign will be negative, minus WL square by 12, and it will be plus WL square by 12. Okay, now I will discuss some special case. So all of us, we generally do a great mistake. Suppose here it is a beam, one end fixed here, another hinge support here, another hinge support here, another hinge support here. So what it is, A, B, C, D. So generally what we do in this case, suppose for span AB, we fix this span. Suppose it is here, it is carries a UDL, it is carrying say point load, it also carrying say point load, so P, it is Q. So what we do in case of this span AB, so we fix this two end, and we calculate the fixed end moment, we calculate the fixed end moment. So in case of the end span, this is a CD end span. In case of end span, we also fix these two ends and we find the fixed end moment, but it is not correct. It is not correct because for Higgs, for the end span, so this point D will not carry any moment. So it's a great mistake, so we generally done. So now I will discuss here for end span. Okay, suppose here a beam section is here AB. Okay, suppose it is C, A, B and C beam is here. So in this case it is a hinge support, it is a hinge support. So for here we have to find out the value of MAB. It is, as it is end span, for end span the formula will be changed. That will be FEM AB, fixed end moment from A to B, plus 3EI by delta plus theta A minus delta by L. So we generally use this equation because here one unknown is here. One unknown is there, only theta A. But if we use this equation, suppose if we use this equation, so here it is two unknowns, theta A and theta B. But if we use this equation for end span, here will be generally one unknown, that is the theta A. So for end span we will generally use this equation, MAB equals to FEMBA plus 3EI by L into theta A minus delta by L. Okay, so now suppose it is a beam ABC and the portion BC carrying a uniformly distributed load, suppose it is W kilonewton per meter length. Okay, it is L, suppose it's L. So as it is end span, so most of us generally we take this portion BC and we fixed the two ends and we calculate this value fixed end moment minus WL square by 12 and it is a plus WL square by 12, but it is not correct. It is not correct. For if it was in case of intermediate span, that was correct for this, but in case of end span it is not correct. So what will be the fixed end moment for in this case? Okay, I will discuss here. So I will take a simple example. Okay, suppose a beam is here, AB, one end fixed, another is the hinge. Okay, so P load is acting here, total length is L, this length is total length is L. Okay, so what will be the value of the fixed end moment? So FEMAB we have to evaluate. Okay, as now see, if we fixed these two ends, now one thing remember here, this last hinge, end hinge will not carry any moment. Okay, that means moment at this point will be 0. Okay, so if we take this beam portion and we fixed these two ends and we put the load here, P load here, we apply load P here. So for fixed end moment will be PL by 8 and its sign will be PL by 8 and its value will be negative PL by 8. Okay, so we take another section or another beam, that is the length is L and here one end fixed and another end is hinged, and we applying a anti-clockwise load here. It's clockwise load, it is a moment is PL by 8, it is positive moment. Okay, and it is we are applying a negative moment PL by 8. So if we apply a negative moment PL by 8, half of the moment will carry over at the fixed end. Okay, carry over at the fixed end. So what will be the moment? So moment at the fixed end will be PL by 16, that is half. Okay, half of the PL by 8 moment will carry at this fixed end. So if we add these two beam, if we will add these two beam, so it will be the similar to this one, similar to this one. Okay, so moment at this fixed end will be PL by 8, PL by 8 plus PL by 16, that is a 3 PL by 16, and the Hing's point net moment will be here P minus PL by 8 plus PL by 8, so it will be 0. So fixed end moment for AB from A to B will be 3 PL by 16. So many exam it is asked what is the value of the fixed end moment for this type of structure, this type of cases. Okay, now I'll discuss some standard cases for fixed end moment. So we have to remember it, okay, because if we use the slope deflection method, so we needed fixed end moment. Suppose one beam is here, it is two ends is fixed, suppose it is A, it's B. A load P is acting at the midpoint, that is the L by 2, it is also L by 2, and total length is L. So one moment is acting here, it is clockwise, that's why the value will be positive, that is the PL by 8, and another moment is acting here, that is the minus PL by 8. Okay, in case of the concentrated load. Now another case, two ends is fixed and it's carrying a uniformly distributed load W kilonewton per meter length. So what will be the fixed end moment? Fixed end moment will be WL square by 12, WL square by 12, and it will be negative as it is anti-clockwise, and it will be the positive WL square by 12 plus WL square by 12. Okay, now another case, its one end is fixed and another end is hinged, and it's carrying a load of so the moment of this end will be WL square by 8. Okay, now another case is here, this end is fixed, another end is fixed, and a load is acting, P load is acting from A at a distance A and B at a distance from B. So the fixed end moment will be PBA square by L square, and it will be PAB square by L square. Okay, so all this end condition is enough for, and also another case is also here, one end is fixed and another end is hinged, and one load P is acting at the midpoint. So fixed end will be 3 PL by 16. I have discussed it earlier. Okay, so it's enough for slope deflection method. Okay, so now I will discuss about a problem. So suppose it's a beam A, B and C. Portion AB whose end A is fixed, B is hinged and C is also hinged. So AB portion carrying a load 3 kilonewton per meter and its length is 20 meter, and a load 12 kilonewton is acting at 8 meter from B and C, that is acting at the midpoint, and its EI value is constant. Okay, EI value is constant. So first of all we will take end span. Okay, first of all we will take end span, that means span AB. Okay, span AB. So for span AB, MAB, we know that MAB, that is the moment at the point A, will be FEMAB, fixed end moment from A to B, plus 2 EI by L, L is the 20 meter length, and plus 2 theta A plus theta B minus C delta by L, and we know that theta for the fixed point will be 0. So value of the theta A will be 0. And here first of all, as we are taking this portion AB, so first of all we have to fix these two end. Okay, we have to fix these two end, and from this we have to find out the end moment. Okay, so it is A, it is B. So end moment as it is clockwise, so value will be WL square by 12, and it is anti-clockwise, that's why W, the fixed end moment FEM AB from A to B will be WL square by 12, and it will be minus. Okay, so here I have already done this calculation here. So WL square by 12, as it is W is 3 and length is 20 and it is 12, W square 12, so it will be the 100 kilonewton meter. Okay, 100 kilonewton meter. So if we put this value, it will come here W square by 12 plus 2ei theta, and here we know that at fixed end value of the theta will be 0, and only one unknown is here, there is a theta B. Okay, so if we simplify, it will come MAB equals to minus 100 plus EI by 10 theta B. This is the number one equation. Now for span AB, we have to find out the moment MBA from B to A, from B to, that is the FEMBA plus 2EI by L plus 2 theta B. Previously as it was from A to B, that's why in this case it was 2 theta A plus B, and as it is from B to A, that's why it will be 2 theta B plus theta A minus 3 delta by L. Here the value of delta will be 0 because the support is fixed, so no support is shifting here, that is there will be no deflection, and delta will be 0. Okay, that's why this value will be 0. Okay, so this is the another equation. So it is coming here in this way. Now similarly for the portion BC, as it is end span, so we will use this equation FEM BC from B to C, FEM BC plus 3 EI by delta plus theta B minus delta by L. Okay, here also delta is 0, no deflection is here, delta is 0, and here FEM BC, and we know, suppose this is it was a problem, that is the BC, portion BC, as it is end span, so we cannot fix the two ends because it is wrong, we cannot fix the two ends. So what we will do here, we will fix one end, and its payload is acting here, it is the hinge support is here, and we know that this fixed end moment will be 3PL by 16. Here P is the 12 and L is the 16. Okay, so we have to put this, and this at this point moment will be 0. Fixed end moment at the point C will be 0. Okay, so now if we put here the value 3PL by 16 plus 3EI by L at theta B minus 0, that is the 3 into P value is 12 into 16 by 16, that is we get FEM BC is 36 plus 3EI by 16 theta B. This is the number 3 equation, and theta MCB, that is the moment from C to B, will be 0 as it is the end span and it's a hinge. Okay, endings will not carry any moment, so that's why MCB will be directly 0. Now friends, it was our problem A, B, C. So A portion is carrying say uniform distributed load, and BC portion carrying say concentrated load acting at the midpoint, that is 8 meter from point B and 8 meter from point C. Okay, and magnitude of this force is 12 kilonewton. Okay, so now what we have to do, that is we have to do we have three equation. MBA equals to 100 plus EI by 5 theta B. MBC is also here, MAB is also here. So now next step is we have to prepare an equilibrium equation. What is the equilibrium equation? Equilibrium equation is nothing but moment from B to A. That means that is the Higgs moment from B to A and moment from B to C will be 0. Net moment from B to A and B to C will be 0 because it is pin joint, so it cannot carry any moment, so net moment will be 0. So we will, what we will here, that is we will add MAB from MBA from a moment from B to A and moment from B to C will be 0. That is the equilibrium equation, and from this equilibrium equation we will find the value of theta B equals to something, suppose x, and we have to put this value of theta B from equation number 1. If we put the value of theta B here, we will get moment at the point BA and moment at the point BC, moment at the point AB. Okay, so we'll get this moment. Okay, so now briefly we can say that for slope deflection method, first of all we have to find out the fixed end moment. After that we have to prepare the slope deflection equation. After that we have to prepare equilibrium equation, and after preparation of equilibrium equation, from that we will find the value of the unknown theta, delta, or anything. Okay, and moment. So after solution of this equilibrium equation we will get the final moment, and after final moment we will put the bending moment diagram. Okay, thank you. In my next lecture I will discuss about so many problems related to the slope deflection method. Okay, thank you guys.